Okay, now in the spirit of tying things together, we're now going to relate injective linear transformations to the notion of linear independence. And the main theorem of this section is here, and the content of this theorem says that a injective linear transformation maps linearly independent sets to linearly independent sets. I could also say that injective linear transformations preserve linear independence. If you go back to this picture up here, see if we can find his cartoon, the one with injective. Here's injective right now. So if we have a linearly independent set here, if these guys are linearly independent, and each one of these maps to uniquely to some guy over here, then these guys will also be linearly independent. You might say, what's the big deal? But it does have a lot to do with, we know that linear independence has a lot to do with solution sets. So the fact that linearly independent vectors map to linearly independent vectors is in fact a big deal. So let's see how that works. Go back to this. We've covered a lot since then, haven't we? Okay. So what that means is that if that linear independent sets map to linear independent sets. The best way to prove this is you're going to prove the contrapositive. Then say that if you have a non-linearly independent set, that is a linearly dependent set, you say linear dependent sets come from linearly dependent sets. Okay. Here it says linearly independent sets map to linearly independent sets. If you think of that in the backwards direction, that says that linearly dependent sets come from linear dependent sets. So that's what he's going to do here. Suppose we have a linear dependence relation among the images of your vectors. Okay. Now, by using the linearity property, we can write this linear combination of images as the image of the linear combination. Okay, so we have t of this particular vector is equal to 0. Well, what does that mean? That means that this vector is in t inverse of 0, which is the same thing as saying that this vector is in the kernel. Now, if this vector is in the kernel, if we have a injective linear transformation, then the only vector in the kernel is the 0 vector. So that we get that, in fact, this linear combination of vectors in U, which is in the domain, must be the 0 vector. So what have we shown? We've shown that linear dependence comes from linear dependence, which is the same thing as saying linear independence maps to linear independence. Okay, so that establishes this theorem. All right, now we know that linear independence is closely tied up with the notion of basis. Basis is a linearly independent set. So suppose we have a basis of U, and suppose we have a linear transformation from U to V, then the linear transformation is injective if and only if the images of this basis is still a basis. Okay. Now we can prove this one way, that if T is injective, then, I'm sorry, it's not still a basis, it's a linearly independent subset. It may not map onto all of V. Remember the cartoon picture where they had some vectors mapping to vectors here, but there might be a few vectors down here that are not here. So let me reiterate that T is injective if and only if the images of the basis are a linearly independent subset of V. Not necessarily a basis of V, but a linearly independent subset. Now we know, we just showed that if T is injective, then it maps linearly independent sets to linearly independent sets. Okay, so that gives us the only if part. The T is injective implies that the image of the basis is linearly independent subset. On the other hand, suppose that the images of the basis set are linearly independent. We want to show that T is injective. So we want to show that T of U is equal to 0 implies U is equal to 0. Okay. All right. Now, if T of U is equal to 0, U is in the domain, so U must be a linear combination of basis vectors. We write U as that linear combination. And we spread that linear combination apart using the linearity property to make it a linear combination of image vectors. Okay. But we're assuming that these vectors are linearly independent. If these are linearly independent, the only way to make this 0 is if all of the A's are 0. And if all of the A's are 0, then U itself must be 0 because it's a linear combination where all the coefficients are 0. So that gives you the other way. It shows that linear independence of the image of the basis is equivalent to an injective linear transformation. All right, so continuing in the spirit of relating new things to old, let's relate injective linear transformation to dimension. Here's the theorem. Suppose you have a linear transformation that maps a vector space U to a vector space V, and T is injective. Then the dimension of U is less than or equal to the dimension of V. Now this makes a lot of sense based on the theorem that we just showed, because if we have U1 up to UN, which is a basis of, if this is a basis, this maps to TU1 up to TUN. So that's this is linearly independent. Now we know that a linearly independent set can be extended to a basis of V. So what does that mean? That means the basis of V must have at least as many vectors as there are vectors here. So that means that the dimension of V must be at least as big as n. So that's the substance of this proof here. I have an example here. All right. So notice that then that if the dimension of V is smaller than the dimension of U, then you cannot possibly have an injective linear transformation. Okay. So if the dimension, so that's exactly what you have in this case. Here you have M23 maps to C4. The dimension of M23 is 6. It's bigger than 4. So T cannot possibly be injective. Okay. So you can't have an injective map that maps from a bigger vector space into a smaller vector space. All right, now we've talked about, you know about composition of functions, and linear transformations are functions, so let's consider composition of injective linear transformations. It turns out that the composition of injective linear transformations is itself an injective linear transformation. And you can prove that directly from the definition of injective. Supposing that the composition applied to a vector is equal to the composition applied to a different vector, then one by one we get that since S is injective, that means that whatever's inside S here must be equal to whatever's inside S here. That gives me T of X equal to T of Y. Then since T is injective, then whatever's inside here must be equal to whatever's inside here. So X must be equal to Y. Again, if you've had functions in discrete math, you know that the composition of one-to-one functions is a one-to-one. And that finishes this section on injective linear transformations.